All right, I think we can get started. We have more than 25 people now. Hello, everyone. Welcome to Penn State CTSI BERD seminar series for this new semester. This is actually the first seminar for this fall semester. And my name is Jay Zhu. I will be the host for today. And for this fall semester, this BERD seminar will be hosted by Dr. Lan Kong, Dr. Terry Murphy, and myself. We are all faculty members in the Department of Public Health Sciences. And today, because Dr. Murphy is today's speaker, so I will be the only host. And this is a list of the topics for this fall semester. Basically, those are some selected biostat or epidemiology topics that we think might be useful for your research. You can go to this website, ctsi.psu.edu, and then go to research support seminars to find more details about the future seminars. And let me just go through some basic logistics for this seminar. The usual setting is it's set up as a webinar. So today's setting, for some reason, it's a little different. It's actually set up as a regular Zoom meeting. So you can, as you can see, that we didn't really mute everybody, but like in a regular setting, the attendees are muted. So I will ask you to mute at least during Dr. Murphy's lecture, and if you at the end for the Q&A, you are free to ask questions. And if you are registered attendees, you will actually receive the slides, recording, link, and a feedback survey after the seminar. Today, we are very happy to have Dr. Terry Murphy here. And Dr. Murphy joined Penn State 18 months ago as a professor of biostat at the Penn State College of Medicine. Previously, he worked in the Yale program on aging and directed the biostat core of the Yale Claude D. Pepper Old Americans Independence Center. Most of his work has focused on longitudinal analysis of observational data, and his research interests include a wide variety of analytical approaches, such as a spatial model, complex survey design, Bayesian method, and joint models. Dr. Murphy has published more than 150 peer-reviewed papers and made significant contributions to the development and application of a statistical method for geriatrics research. His current interest is in longitudinal analysis that use structure equation models to address issues such as reverse causality and measurement error in a multivariate framework. Today, Dr. Murphy will talk about the design and analysis of complex surveys studies. So, Terry, I will stop sharing my screen, and you can go ahead start.
Wonderful. Thank you for that very kind introduction, and I welcome you all, and I thank you for spending your precious hour on this beautiful fall day with us to learn a little bit about complex survey designs. You'll notice that I've tweaked the title a little bit because I'm more talking about taking existing complex surveys and showing you how to analyze them and interpret some of those findings. I do go into some of the design aspects, but I don't actually show you how to design these. So I just want to set those expectations early. This is based on work with colleagues of mine, Jason Falvey, who was with us at Yale and is now at the University of Maryland at their Pepper Center, and Lauren Ferrante, who is at Yale still. Okay, so here's an outline. First of all, I'm going to talk about another longitudinal study that I worked on for over 15 years called the Precipitating Events Project. And it's a wonderful data set, and we've gotten over 100 publications from that data set because it's so rich. But it has one big limitation that we're going to talk about, and that's going to motivate us. Then I'm going to talk about some of the design aspects of complex surveys, what makes them different from some little survey that you may create in REDCap or on your own with one of these websites. And I'm going to talk about several examples using a very nice complex survey called the National Health and Aging Trends Study, also known as NHATS, which is designed at Johns Hopkins, and they continue to administrate it along with help from some colleagues at the University of Michigan. And one of the examples I'll look at is the effect of social isolation on outcomes among critically ill older persons, and then we'll have a few conclusions. So let me start by describing this motivating example. It's based on a study called the Precipitating Events Project. The principal investigator is Dr. Thomas Gill at Yale, and it's a prospective cohort study that started with 754 persons, 70 and older, who were non-disabled at the beginning. When I say disabled, it meant they didn't need help with any of their 4 basic activities of daily living. Those are feeding, dressing, transferring. I tend to mix them up, but anyway, there are 4 basic activities that if you need help with any of those, you are considered to have some level of disability, functional disability. The objective of this study was to elucidate the mechanisms underlying functional decline among community living older persons. We didn't look at folks in nursing home because we're trying to understand the natural process before people get too far downstream. So here's a slide showing the structure of this study. It started in 1998. It is continuing today in 2023 with these 754 older adults. The hallmark of this study is that every month we have phone interviews where we interview these persons, and we get an assessment of their disability over 13 functional activities: basic activities of daily living, instrumental activities of daily living, and mobility. And every 18 months, we have a face-to-face interview at their houses where we collect lots of variables that usually serve as explanatory variables. Typically, our outcomes are some measure of the disability, since that's the whole purpose of this study. Now, this is a very nice study. In some regards, it was really well designed because the persons who declined to participate did not differ significantly from those who were enrolled. It is very reflective of Greater New Haven County. That's a county in southwestern Connecticut, about an hour and a half north of New York City, which is in many ways representative of the country, but not in terms of race, okay? And so also, because the data is gathered only from that area, Connecticut is a small state, it really doesn't allow you to draw inference across the entire nation. It only allows you to draw inference around Greater New Haven. So that's my motivation. So even though we used that data set to great purpose, we've got over 100 papers published in very good journals, every single time we write up the results, we have to put a qualifier, but we can't infer to the whole country. We can only infer to Greater New Haven area. So why use a complex survey design? Well, because usually it's too expensive to say randomly sample across a country as big as the US. So you use a survey design. You need to oversample special subgroups that are historically underrepresented. And the example I present later is going to be from NHATS, the National Health and Aging Trends Study. This study oversamples African Americans and persons of age greater than or equal to 90 years, because both these groups are typically underrepresented in national surveys on aging. So I define here simple random sampling. That's going to be kind of a reference that we push off of many times. So what is a complex survey design? It's a probability sample developed using techniques other than simple random sampling. So it has more complex sampling characteristics. These typically involve stratification, clustering, and weighting. These three design parameters help reduce costs and or improve precision. And we'll talk about that. So this is just a little bit of the design material that I'll be talking about today. So if you're looking at a complex survey design, NHANES, NHATS, there are many of them, the Women's Health Study, Health ABC. If you drill down a little and you want to analyze these, and they're generally publicly available, you will want to familiarize yourself with the strata, the cluster, and the weighting variables that come with the data. So it's a probability sample. That means each subject has a known non-zero probability of selection. Now, the weights allow you to create unbiased point estimates. So let me illustrate this. If you want to describe, say, the age of people 65 and over in NHATS, the weights multiply each individual observation so that the pseudo population, the weighted population that you will perform analysis on, is truly representative of the overall national population. So it will account for the oversampling of African Americans and of folks 90 and over. But these weights allow you to draw inference to the national population, even though you're not sampling everyone in the population. Variances are estimated from the data, and because of the sophisticated sampling design, which has strata and clusters, it has to account for those design features when it's calculating the variance of the estimates. So here are these three fundamental design characteristics of any complex survey design. Stratification. Stratification relative to simple random sampling actually improves the efficiency of your estimates. What does that mean? It means it lowers the variability. It makes them a little more precise. Clustering generally raises variability, so that injects a little more noise. And weighting, it does reduce bias in the estimates, as I was saying. The important thing to realize about the weighting is these are designed to adjust for selection, because you're selecting people within clusters who are within strata. So there's always a chance, every single person you sample has a probability of being selected and a probability of non-responding, including those who maybe drop out or die during the process. There's also the possibility to use data from the overall population that comes to you externally from the survey design. So even though you do a nice complex survey design that allows you to draw inference to the whole country, you're definitely not sampling the whole country. So you can find other sources of data from the population that can be injected into the analysis to help reduce bias. Now, how do these design characteristics, stratification, clustering, and weighting, how do they contribute to the variance of the estimates? Remember, we're estimating associations between characteristics of these persons who contribute to the national population. Well, stratification actually lowers variance, clustering raises variance, and weighting raises variance. So you can kind of guess that overall, relative to simple random sampling, the use of a complex survey design is going to give you, on average, greater variance. Okay. Now, at a very simple level, anything you try to estimate from this survey, and here I'm going to call this theta hat. The hat theta is often used in statistics to represent a parameter of interest, and hat means you're estimating it from data. You estimate some point estimate, and then you also generate a confidence interval. And so the theta hat tells you the point estimate, and the confidence interval is generally a t-statistic times a measure of robust standard error for theta hat, okay? And the robust standard error, that accounts for the variance injected into the process by the strata, the cluster, and the weights. So a simple approximation for the degrees of freedom, remember in that prior slide, here we had degrees of freedom, right? So you can look up a t-statistic, the critical value for a t-statistic in a table of t-values, but you have to know the degrees of freedom. Well, there's a very quick and easy, if you can subtract the number of strata from the number of clusters, or you can use the number of replicates minus 1. So it's not easy to come up with the degrees of freedom, even though it's this complex survey design. So if you want to do some regression, you will use weighted least squares for theta hat. You will use the typical checks for model fit that we teach in courses of regression. The special software will evaluate t-tests of individual parameters, and it can also calculate walled or transformed f-tests when there are multi-parameter hypotheses. When we're estimating the variance of these parameters, the two most common approaches are Taylor linearization, and that's the simplest and fastest. The other methods are based on resampling techniques. There is a jackknife repeated replication and a balanced repeated replication, and there are also bootstrapping methods. Now, if you don't have anything like repeated measures that require a special analytical approach, then you can usually use Taylor linearization. If you have more complex aspects contributing to your overall variance, such as repeated measures then you'll probably want to use one of these resampling methods. When you use these two repeated replicate methods, the jackknife and the balanced, each replicate has a unique weight, and you would recalculate, you would re-estimate a parameter of interest over these replicates with their weights, and then you would derive standard errors and confidence limits. I want to put a plug in for this book. The second author, Brady West, I took a course with him a year or so ago, and a wonderful instructor. This is very easy to read. There's very little math, and it provides a real wealth of conceptual foundation to help you understand how these things work. So very readable. It has code in SAS, in R, in Stata. So if you're ever, need to do a crash course in this stuff, I highly recommend this book. Okay, now I'm going to talk about NHATS. NHATS, as we said earlier, National Health and Aging Trends Study. You heard in the introduction that I spent the last 17 years at Yale doing longitudinal studies of geriatric outcomes. So NHATS was designed by some of our friends at Hopkins, and it's a nationally representative sample of Medicare beneficiaries who are 65 and older. Now, some of you folks are from different countries. Medicare is the closest thing the US comes to kind of a national health plan. Folks 65 and over 95% of us, I'm not there yet, but those of us who are 65 and over, 95% of us get our health care from Medicare, which is administered by the federal government, okay? So NHATS is designed to represent the Medicare population, and it has geographical clustering within regional strata. So regions are chunks of the larger United States of America. Counties are sampled from within those regions. Zip codes, those are postal codes, are sampled within the counties, and then individual persons, SP, sampled persons, are sampled within the zip codes. The first NHATS cohort started in 2011. They have about 8,000 persons. So think of that. This is 8,000 persons to represent close to 100 million persons. So it's a very careful design. There was a second cohort started in 2015, and there are yearly observations. As we said earlier, it oversamples African Americans and very old people. And the selection probabilities, meaning the weights, differ by age and race. Now, you need special software to properly analyze complex survey designs. SAS does a nice job of it, but you have to use the special regs that start with survey. So Proc Survey Reg allows you to do regular linear regression. Survey Freak allows you to build 2x2 tables. And Survey PH Reg allows you to do Cox regression. Okay. Notice that there's not really an option here for count models. Okay. SAS callable Sudan. Okay. Many of the analyses I've done have used count models. And so I've had to buy SAS callable Sudan, which is very similar, its syntax with SAS. So it's pretty easy to use if you already know SAS. Stata, so Brady West, who taught the course I took, this is his favorite package for these things. R is very popular. Of course, it's free. You can use the survey package. And M+, it's kind of expensive. It's not hard to use, but it can combine weights and structural equation modeling. So in some ways, M+ has the best overall collection of features. Here's the example I'm going to dwell on. This is a paper we published in JAMA Internal Medicine a few years ago. First author is Jason Falvey. The senior author is Lauren, and I'm here. The impact of social isolation on disability and mortality among older survivors of critical illness. So critical illness among older adults is associated with morbidity. That means chronic diseases and death. Geriatric vulnerabilities such as frailty and cognitive impairment are associated with higher risk of death and higher risk of disability, but not much is known about social risk factors such as social isolation. One of the sad parts about aging is more of our friends and loved ones die, and as we out-survive folks, we often tend to be alone. So it often reflects a lack of meaningful social ties, and nearly 8 million people are officially socially isolated, and it's associated with a higher risk of death, okay? So this study started just before COVID came, but we feel like the results are more important now since COVID, because within the first month of COVID, loneliness among older folks increased by 20 to 30%, and emotional distress tripled. I have a list of references at the end. Here was our research question. Is social isolation associated with greater burden of disability and higher mortality after critical illness? And we want to be able to infer on a national basis. You'll remember I started with the PEP study, which is a magnificent study, but it could not make inference on a national basis because it was not designed to do so. How does NHATS become so useful? It uses Medicare-linked data. It can link to Medicare. Now, Medicare, because it pays for all the healthcare of older folks, we can get the billing records. Who was critically ill? What treatments did they receive? We identified critical illness hospitalizations using some of those revenue codes in the inpatient file. We used a scale of social isolation developed by Pohl and colleagues, and it's based on talking to either a live-in partner or spouse, and it asks about how they talked with family and friends, and whether they belong to any community, such as a religious group or a social club. It's an ordinal scale, 0 to 6. Higher scores mean more social isolation, okay? We used a vertical data structure, meaning that in the data we analyze, each person year is a record. We had a total of just under 40,000 person rounds. Now, this is one of the interesting things about complex survey. We only had 648 of these that were person admissions, in other words, older persons admitted to the hospital with time in the ICU. So out of 40,000 person years of data, we have less than 700 of these for whom we have measures of disability before and after. Now, disability in aging studies is hugely important because while everyone wants to live long, right after wanting to be alive comes a desire to be independent. Most older folks, the thing they value more than anything is maintaining their independence. And so disability, functional disability, means I need help to dress, I need help to toilet. So this is a hugely important outcome to older folks. We also studied mortality. We had a few more people eligible for mortality than for disability because people who were already at maximum functional disability were not eligible for our analysis. There were a few folks who in different years had different ICU admissions, okay? Here's a consort diagram. We start off with 1,800 ICU admissions. We keep only the first one for each interval. That shaves off a few hundred. We throw out those who don't have an assessment of disability prior to admission, because that's such an important characteristic for us. And then we look at a mortality cohort, and then we finally get a slightly smaller disability cohort, because here we're looking at their measure of disability in the year after hospitalization. So folks who died or went to hospice or reached the maximum disability were no longer eligible for this second outcome. So we were looking at community dwelling folks. We wanted this pre-ICU assessment of their functional disability. And we had data over a 7-year period, okay? And we were looking for, we wanted the pre-admission measure of social isolation. That's this whole scale that goes from 0 to 6. We wanted to look at its association with the count of disability a year after the ICU, okay? There was a very small amount of missing interviews that we considered missing, not at random. Otherwise, we multiply imputed. Okay, now, the count of disability, remember, it goes from 0 to 13. We used a Poisson regression in the SAS callable Sudan. Some of you who may have taken a course with me would say, well, why didn't you use a negative binomial? Because that's usually a better distribution. Well, the specialized software in SAS doesn't allow you to do a negative binomial. Okay, so when you start doing very specialized data like this, you don't always have all the software options that you might have otherwise. GEE means generalized estimating equations. It's a nice way to account for the correlation among those persons who contributed more than one ICU admission over the 7 years of follow-up. We also did some sensitivity analyses. So here is the post-ICU number of disabilities in the blue boxes. The orange dots are the pre-ICU number of disabilities, and we compare pre and post as we go up the scale of social isolation. Notice that you have much smaller sample sizes the year after the ICU, especially among folks with no disability or with almost full disability. These sample sizes are much smaller at the extremes. That's why the confidence intervals are so big. But otherwise, you see this nice pattern that suggests, wow, there really is a significantly higher disability among older folks hospitalized for critical illness in the year after that goes along monotonically with increasing social isolation. Remember, we're only using 648 observations, but based on the weights, these represent almost 4 million admissions. So here's what we found. We found that for incremental rise in your social isolation prior to admission, your count of disability went up by about 7%. So it had a p-value of 0.029, and this was done using SAS callable Sudan. So positive association, higher social isolation, higher functional disability a year after critical illness of older persons. Here's what SAS callable code looks like. You notice it looks a lot like SAS, but there's no proc log link in SAS. It does a few little things differently. If you have multiple imputations, it assumes you have consecutively numbered data sets that it will go through. Here's the weights. You have to use a subpop command to discern the 648 observations from the rest of the 40,000 rows of data. Here was our second outcome, was time to death within 1 year of discharge. We did Cox regression. We were able to use the SAS-Proc pH survey reg. We used the Taylor linearization for the variance estimation, and we did some sensitivity analyses. Notice here the Kaplan-Meier. You have the 6 levels of social isolation prior to admission, and notice that the survival probability goes down monotonically. So very, very nice, clear result here. So here we have these 997 hospitalizations that led to death within a year, and they represented nearly 6 million person admissions across the country. So for each incremental rise in the count of social isolation prior to hospital admission, the hazard of death within a year went up by 14%. Very high p-value, okay? This did not have adjustment of standard error for multiple observations because SAS-Proc pH reg doesn't allow that, okay? So here's Proc survey reg. This is just regular old SAS, okay? Notice that because I used here as a way of getting robust errors, I used the balance repeated replicates. So what it is, for every row of data, there are 56 additional columns that represent unique weights corresponding to 56 replicates of each row of data. And this is one of those replicated techniques that allows you to get an estimate of robust error. So here are the sensitivity analyses. If I took just the first observations from persons, very similar results. If I use the robust errors, I get nearly identical results. If I use the bootstrap option for variance, I get almost identical results. In fact, the most conservative are really here with the balanced repeated replicates. So here was a paper we got in JAMA Surgery where we took NHATS data and we looked at folks who had had major surgery, again, over 2011 through, I think, about 2019. And, you know, it got into JAMA Surgery, which is one of the top rated surgery journals, okay? And then more recently, I developed a risk prediction model for persistent functional impairment among folks who survive critical illness and then are discharged if they have persistent functional decline 6 months after discharge. And in fact, because we used NHATS, it was 1 year after discharge. I was able to develop a model whose coefficients represent the national associations. So this is another thing you can do with a complex survey design. You can build a risk prediction model and you can make a justifiable claim that your model coefficients are nationally representative, okay? So a couple concluding comments. If you want to make national inference, and the bigger journals, the higher tier journals are really very interested in making national inference because it, of course, describes the country, but it also avoids local effects that you might get, such as just focusing on New Haven, Connecticut. The weights enable unbiased estimates, point estimates of associations. They address the probabilities of non-response and unequal selection. And the variance estimates can account for complex sampling. So there's a lot of bells and whistles here that lead to more reproducible research. Here are a few acknowledgements. These were folks mostly at Yale, but this is the CTSI grant that I now cite from Penn State. And here's a list of references if you want to look up anything that I talked about. Okay, so I want to thank you for your attention. It's not easy to listen to a talk like this at 4 p.m. I can't see most of you, but I'm hoping you're awake. And now let's open up the floor for questions.
Yeah, thank you. Thank you very much, Terry. So for our audience, if you have question, because of the setting, it's a regular Zoom meeting. You can actually go ahead and talk, or if you prefer, we don't really have a Q&A box, but there's a chat box that you can type.
I'll make one comment. A year ago, Lan Kong was listening, and she asked me a question like, what if someone wants to create their own complex survey design? And I didn't really have a good question. I gave almost this identical talk a year ago. Mm-hmm. And I wrote to Brady West and I said, what does one do? You know? And he said, it's really not that hard. He said, there are courses such as Coursera. I've never taken a Coursera course, but
Coursera, yeah.
Yeah, he says you can find one, and if you have some insight as to what I talked about, the weights and the strata and the clustering, it's really not hard to design your own complex survey design. So I'll throw that out. A course in Coursera with the book that I cite, you could probably have a very strong place to start.
Yeah, I guess like national survey design is not just a one man's job. It's actually involves expertise in different areas, right?
Yes, there's a center at Michigan. That's where Brady West works, which is it's like a statistical center devoted to complex survey design. So
okay.
They have a huge amount of expertise, and some of the people who designed this study at Hopkins actually moved over to Michigan. So there's a lot of cross-fertilization between Hopkins and Michigan with these studies. But you're right. If you want to do like a really ambitious thing like NHATs, you're probably going to have to go to the experts.
Yeah.
Hello, Terry. This is Moso speaking. Thank you for a great talk. I have a question. Like how did you deal with the missing data?
Great question. So just like with any study, I try to very quickly get my head around how much missing data is there, and can it reasonably be assumed to be missing at random? For instance, in NHATs and in the PEP study earlier, our practice, and I think this is not uncommon, if someone misses a whole interview, we tend to think of that as missing not at random. We think there's some reason why they couldn't make a whole interview. But if they're missing a few things within an interview, we usually assume that's missing at random. And if it is missing at random, then there's a proc called proc survey impute. And you can use that, and it uses the strata, the cluster, and the weights under the assumption of missing at random to fill in the missing values. So there are imputation tools that take into consideration all the design parameters, again, contingent upon the plausibility of missing at random.
Okay, thank you.
Sure. Thank you for the question and your kind remark.
Yeah, thank you, Dr. Chow. Yeah, your question is actually one of the questions that I want to discuss with Dr. Murphy. So yeah, just a follow up to this missing value question. So before you actually run the main body of the analysis, do you actually do some exploratory study to check if missing at random is a reasonable assumption? Like, for example, do you actually check whether or not the missing value is associated with some social economic factors to see if this assumption is really violated before you actually run the formal analysis?
So, missing data, there's a lot of room for kind of individual practice, right? So I'll just describe what I usually do. I usually like to look at, histograms, the distributions of the values. And then I also like to look at the patterns of missingness. And I also like to talk to some of my colleagues who are clinical experts. For instance, I am never comfortable imputing race. Okay, I don't believe. So I have two conceptual guides for missing at random. The first is the variable with the missingness, is it reasonable to estimate the missing values with information you can draw from other measured variables? So if the answer is yes, then I say, okay, you've met the first necessary but not sufficient condition for missing at random. The second one is, sorry, I went blank. Yeah, so you have to reasonably be able to estimate it. And second, do we have reason to believe that if it's missing because of a value that someone doesn't want to report? For instance, in economics, there's often missingness at the very low end of the scale and the high end of the scale because people are embarrassed or secretive about wanting to share very low income or very high income. So that's a case where it's clearly missing not at random because the missingness is directly associated with the value itself that would have been reported. So if a variable, for instance, like race to me, it can't be reasonably estimated from the other measurable variables, okay? And income, I won't impute that because it's almost never missing at random. Now for income, NHATS provides imputed income values because there's so much missingness, but they've used very sophisticated models that are missing not at random models designed to take care of that. And so for me, if the missing variable can be reasonably modeled, and if clearly the missing values are not, the missingness is not tied to the exact values themselves, then in my mind, it passes my test for missing at random. And I check this out with the content experts. And if they agree, then I go ahead and use, I assume missing at random and I use multiple imputation.
Okay. Yeah.
So,
yeah, thank you. Yeah.
Some people might not agree exactly with that, but that's how I do it.
Well, I think different people may have a different approach. There's no right or wrong in this missing value issue. I think here, because you mentioned like for this particular data set, you also have the access of the billing, like the medical bill data. So for example, if the race information is missing on the survey, but you can actually link that person with the medical bill data, probably you can cover part of the missing data from another major data source, right?
Yes. Yeah. I mean, race, age, and sex in NHATS, there's no missingness, right?
Yeah.
I was just kind of talking conceptually. Another example would be in a study I did called Silver. We were modeling readmission after hospitalization for heart attack. I felt we couldn't impute an indicator of chest pain the week before admission because we just don't have that temporally specific information.
Yeah.
Okay. So that was another example where I might have been missing a few people reporting whether or not they had chest pain the week before. That was one I wouldn't feel comfortable imputing.
Yeah, that makes sense. See if our audience have some other questions. Yeah, just feel free to ask.
Hey, Dr. Murphy, can you hear me?
Yes, but speak
Yeah,
a
we
little,
can hear you.
little
Yeah.
soft.
Okay. So thank you, Dr. Murphy, for your kind talk. I have two questions about oversampling you just mentioned in the talk. So the first one is that you mentioned that in the study you participated, you were oversampling some races and some older people, right?
Yes.
So to my understanding, is it because of that you mentioned that I guess it is a cluster centering your a cluster sampling, you're sampling some regions from counties and then some zip code from those regions and then some person in that zip code, right? So I guess
Yes.
it is so is it is one of the oversampling reason is these county the proportion of this races or this age group being different from the larger population?
A lot of the thinking, first of all, help me say your name, Shin Rui.
Yeah, sure.
Is that okay?
Yeah.
You'll forgive my terrible American pronunciation. Okay. So often the oversampling, like in NHATs, of people over 90 and African Americans is because all the prior studies we've had underrepresentation. We've had proportion in all the big surveys and the studies, we've had lower proportions of participants who are African American and lower proportions who are 90 and older than in the general population. So in this study, in order to make sure that we have at least the actual proportion in the population, we oversample, and then afterwards, the weights are adjusted so that even though there's some oversampling happening, in the pseudo population, that's the weighted population in which you run the models, you actually have the true population of African Americans and persons over 90. Okay, so in some ways, it's an overcompensation for past mistakes of survey sampling.
Okay.
Am I answering your question?
Yeah, kind of. So do you mean that based on past experiences, African Americans and older peoples, they are less likely to be sampled to be respondent. So we are trying to get more samples so that if we truly we got more samples from these groups, we can downweighted them, but at least we got enough samples.
Yes, that's exactly what I'm saying, that we can assure ourselves that in our pseudo population, like the larger population, the weighted population, that we are at the same proportion as in the actual US population.
Okay. And the second question is that, so before drawing the samples, we usually make a plan for like what proportion of each races or each age groups we are going to sampling, right? So for instance, in your study, you're planning to oversample African Americans and older people. So how much they are how do you decide how much they are oversampled?
So my only experience is with that first study I mentioned, the PEP study. There we oversampled frail persons, so persons who had no disability but still were frail based on some metrics. We oversampled by about 20%. And so my own experience, what I've heard is between 10 and 20%.
Okay, I see. Thank you. I think that's all my questions.
Thank you for being so courageous and asking a question.
Yeah, thank you, Ray. Any other questions from our audience? I have one more quick question for you, Terry. You mentioned the sensitivity analysis. You listed a table using different statistical approach, having different assumptions, basically. Is this sensitivity analysis usually required as a part of the analysis for this complex survey data?
No,
or it just
no.
depend on the journal?
It depends on the journal, but because I've been in the aging research business for a long time, I'm acutely aware that when you do longitudinal studies of older persons, there's inevitably death. And so death is the classic competing risk where if someone dies, you no longer have their data, right?
Yeah, true.
And there's also something called the healthy survivor effect, right? The people who continue living are not fully representative of everyone. They're actually like super survivors, right?
Yeah.
And so the data you continue collecting from the survivors tends to be somewhat biased, right? And so in my own work, I learned over the years to conduct sensitivity analyses to the competing risk of death because it tends to bias things. And the higher the amount of death, the more it biases things. So myself as a person who models observational data longitudinally, I've gotten in the practice of doing a lot of sensitivity analyses. That said, if you do it proactively, you feel more confident about your work. And if you mention it in the stats section, it tends to proactively disarm some concerns of the statistical reviewers.
Yeah, absolutely. Yeah, I totally agree. Yeah, and
So,
it actually makes the results more robust and the leading conclusions more trustable if you have this part of the analysis.
But using a data set like NHATS, that's a huge boost. Like it's so well respected that if you're using it with the proper techniques, that goes a long way toward reassuring jittery reviewers.
Yeah, agree. All right. It's 5:01. I think we have a very nice talk today, and thank you again, Dr. Murphy. And also, I want to thank you, everyone who attended. So the next webinar will be on the 26th of this month. So I hope to see lots of you on the 26th. All right. Thank you very much. I see you in 2 weeks. Okay. Bye.